Um, I'm very pleased to be here, and thanks. Hmm? Oh, okay. So my name is Elham. I'm currently a staff scientist at Vector Institute. Prior to that, I was a data scientist at RBC. So my colleagues are here, and I also did my PhD and postdoc at University of Toronto and UHN. And the main focus of my PhD was using machine learning for health application. So in terms of the background, my bachelor's and master's are in electrical and computer engineering. So I've been working with signals and signal processing, digital signal processing for a while. And okay, I'm very inspired by the audience, so feel free to correct me if I'm wrong. And so this paper that we are going to review today is somehow, it's a cool paper, one of the three main approaches for generative models, but it's about 5 years old. And in terms of the agenda for today's talk, so I'll give a very small background, and then I'm going to review the paper, and then we can have open discussion at the end on deep generative models. Oops, I should use this one. Okay, so probabilistic graphical models. So our system is a collection of random variables, including observations and latent variables. Observations are the data that we can observe, like images, as in handwritten MNIST images. And, but there are some latent variables that we cannot see, but they have to be inferred from the observation. And when we infer those latent variables, we can generate our data. So the observation might be very complex. Again, as in, for example, face images, all these images, they're complex. And the latent variable might be deep and continuous. So the goal is to learn these parameters that helps us to infer our latent variables. And back to Bayes' theorem, we have the posterior. Sorry. Okay. So we have the posterior, and then our observations are the samples of a true distribution P of x, which we call marginal likelihood, that we want to find, but it's hard to find. And then the way to find this P of x is integrating the likelihood over the entire latent space. So this is the challenge in kind of Bayesian statistic community and machine learning community, because for complex models and big data, it's very hard to compute the posterior or the marginal likelihood. So they are intractable, and if they're intractable, it means that we can use expectation maximization. So there are ways. So, for example, what I mean in complex model and big data, for example, as the case in neural nets. So there are different ways to compute posterior. For example, we can, if the model is tractable, we can use analytical integration, as we do for Gaussian mixture models, for Gaussian processes. But sometimes, when the model is deep, having different layers of transformation, as in deep neural net, we should do approximation. So there are different ways of approximation. We can use stochastic methods, as, for example, sampling, like MCMC Monte Carlo, and then a Markov chain Monte Carlos, or we can do variational. So variational is the scope of this paper. There's a lag. Okay. So what do we mean by variational approximation? So if this is, so the goal here is to approximate our true posterior distribution. So we usually use a family of distributions that are tractable, like Gaussian distribution. And we use this family of distribution to kind of find or approximate our true posterior distribution. So this family of distributions are usually characterized by these phi parameters. They're called variational parameters. And the goal is to find phi that makes Q closer to our true distribution. Any question?
So how we make that possible? Because we don't have the true distribution. So
Exactly. So we don't have the true distribution. So we are using Q. And Q has a tractable, Q is chosen, it's a family of distribution, and it's chosen in a way that we know, for example, we use Gaussian distribution, which is tractable. And we play with these phi parameters to make it closer to the true distribution.
how is this closer to the...
So I'll explain that in the next slide. Was there a question? Okay. So there is a method called a KL divergence, and it's coming from cross-entropy and information theory. So they've been using it in communication for a while. That helps us to minimize, to actually find this problem, find the variational parameters. And what KL divergence does is that it shows how this dissimilarity between the two distributions. So if you can minimize this KL divergence, it means that these two distributions are close. And what it means that how much information you lose if you use a Q instead of P. So you have to minimize this.
The Q distribution is represented by samples, right? Only the samples that we have.
So we are not doing any sampling right now. We are just saying that there is a true distribution, and I want. So
maybe later.
Yeah.
Maybe we'll show up
So I'll
later.
show you.
Oh, okay.
Yeah.
So later.
So we can definitely use, for example, to find Q, we can use MCMC, but it's very slow. That's why this paper does works with the variational lower bound. So the KL divergence is it's very close, like the as I mentioned, information theory and cross entropy. So this is how you define the KL divergence. And if you just use the Bayes theorem, you kind of put the parameters, for example, P z of z given x, you can replace it with the joint distribution, and then the denominator is the marginal likelihood. You will get this. It's very straightforward to do.
Why is this Q over P instead of P over Q?
Because actually, that's a good question. You can't say, because for now, this is the truth, this is the ground truth, and we want to make Q as close as possible to P. So if I put P here, it means that how much information I will lose if I want to make P close to Q. So it matters, the orders are important. And then this integral is called, is the negative of variational lower bound. So variational lower bound is the integration or the expectation of this log with respect to posterior distribution. And you see here is just, so far I'm just replacing this with the variational lower bound, negative minus L. And if I put it here, I will get this. So this is, remember, this is the marginal likelihood. And this KL divergence is always positive. So the marginal likelihood is always greater than L, the lower bound. So that's why it's called lower bound. So if I find the lower bound, it means that I can find the lower bound of the marginal likelihood. That's why it's called lower bound. Clear? Okay. So back to our goal, we want to minimize the KL divergence with respect to variational parameters phi. So P of S, the marginal likelihood, is fixed with respect to variational parameters. So the goal is to maximize L. So, and this is L. And again, so this is the actual expectation of this with regards to Q. So I can rewrite it like this. Again, it's very easy, you know, just again a Bayes theorem. And the reason I'm keeping these two is that I'll explain in the next few slides, but just remember these two equations. Again, I will show them again. So this is my objective, the lower bound that I want to maximize. I want to maximize equation 1 and 2. They're the same, just the representations are different. Okay, so now connection to autoencoders. So this is the loss function or the variational lower bound. So we have this KL divergence plus this expectation. So if we look close, you know, have a closer look, we'll see that what it says is we have, look at this approximation, approximated posterior. So it says that we have a mapping from X to Z, and then this is the reconstruction loss or expectation negative likelihood. So we have a mapping from Z to X. So we have a stochastic encoder here that maps X into a distribution, and then we take samples from this distribution Z, and then we have another stochastic decoder that maps Z onto to X. And remember, like this is pretty much like a neural network on handwritten, on hand digit recognition. For example, there we had P of Y given X. Now we have X given Z. So Z is the input and X is the output. It's reconstructed input. Good. Okay, so just now forget about the variational lower bound just for a moment. So now I'm going to talk about latent variable model. And the reason I put this slide is just to give a rationale on why we are doing that. Say, okay, I can use Gaussian mixture model and can do unsupervised clustering, or for example, from Gaussian mixture model, or I can use PCA or probabilistic PCA or Gaussian process latent variable models to have generative models. So why we are bothering ourselves with using autoencoder? So the reason for that is with all those approaches, traditional, these days they're called traditional approaches, we are limiting ourselves to either linear mapping or in GPLVM. It's non-linear, but it's still, you know, there is just one layer of transformation. But here, if we can use, if we can make benefit of the deep learning model, we can represent complex P of X. And then we can have a complicated conditional dependency. So for example, we can have a one layer of latent variable, stack it to another layer, deeper layer of latent variables. And this way we can represent or model complex data. And the example is that, for example, we can use deep neural net to represent our latent variables. So this is the rationale of why using deep learning models. And back to variational autoencoders. So far, we learned about that lower bound, and we realized that, okay, it's a function of theta and phi. So the goal here is that if I find phi and theta, the optimal phi and theta, so the problem is solved. I'm good, I'm done. So, but the issue is that how, okay, so here, as you see that, yeah, there is a connection to autoencoders, but there is a sampling process involved, and how I can do backpropagation with sampling. So for backpropagation, I need all the nodes to be deterministic. I can't work with random variables.
Excuse me, can you lecture over the sampling thing? Where is the sampling involved exactly?
So far, I'm just connecting that loss function to an autoencoder. So here, So what I'm doing is that as whatever I see here, I try to kind of connect it to what exists in autoencoder. Here, from this scale divergence, I can say that there is a posterior that maps x to z, and then see this is from this this stochastic encoder maps x to I have the distribution. You know, here I have the distribution, and then I take one sample from that distribution, and it will be fed into the decoder. So this is where I'm doing sampling. So these are sampled latent vectors.
Since, for example, you have batches that you're trying to train, so it's like having samples from...
Yeah, I explained that. It's just for...
I'm not sure. Is that correct? Is that understandable?
Yes, you take samples for sure. Yeah, otherwise, because what you're doing right now, that you have input, and then you want to find the posterior distribution for your input. You want to infer those input to their corresponding latent variables, but you don't have those latent variables. What you can do is just you can find its distribution. And then if you want to connect it to an autoencoder, you need to take samples. And then when you take samples from that distribution, it will be fed into the decoder.
What we know about Z, we know just, for example, dimension of the matrix. That's all we know, right?
What do you mean by the dimension? You mean, for example, it's 2D, 3D, 4D?
For example?
Yeah, it's a hyperparameter thing. You can
mapping into a lower dimension, right?
Yeah, the goal here is, as you see it, for reducing the dimension. Yeah.
So the only thing that we know is what is the dimension of the Z, nothing else.
Because here,
yes. So
you can
actually, you know what we know about this? You know, just let's forget about this variational autoencoder. What exists in a regular autoencoder? So just don't think. So this is exactly. Just forget about the stochasticity. Let's say that this is an autoencoder. So autoencoder, the input will be fed into the encoder, a deep encoder, and then there's a bottleneck here that is a latent variable. It compresses the data information, and then it will be fed to the decoder, and you can reconstruct the image. So the difference is that here we are adding a regularizer. We say that, okay, the latent variables can't be everything. They can't occupy the entire, latent space. You are somehow putting restriction around them, like me. There's a bounding box around me. So you should be here. You should be around. You should be kind of close to this distribution. That is my prior. So I make some prior assumption about the distribution of the latent variables, and then I say, okay, the approximated posterior should be close to this distribution. So this is how. Okay.
I just want to add another comment, which is Q here is user defined. You can define as the Gaussian distribution.
Yes, exactly.
And then you can
Q
just try to adjust the
Q is this is how you deal with it. That you say, okay, I want to approximate this posterior with this type of distribution that I know a lot, like Gaussian. We all know about Gaussian. We know that they're attractable. You can do expectations. You can integrate them. So this is how I choose. So actually, let me check. I made some notes. I want to make sure I covered everything. Okay, so right now, it's that variational autoencoder looks very nice, but I still cannot solve it because there's a sampling involved, and I can't do backpropagation. So there's a technique called reparameterization trick that allows you, actually, this is what I have right now. I have the X, I have variational parameters, and then this is the Z that is sampled from this approximated posterior, and then it will be fed into the F, which could be a neural net, whatever. So since this is random, I can do backpropagation. So what I can do is that I can say, okay, I define Z as a deterministic function of X and phi, and then I add another input. I call it epsilon, which is a white noise. And this way, I can still keep a stochasticity, but I can have a deterministic function of the inputs, and I can do backpropagation. So this way, the expectation of f of z with respect to posterior approximation equals this. So I just replaced the z with this deterministic function.
So you're already trying to, again, find a function that shows what is z already, right?
Yes, exactly. So, and the example is, okay. So for example, a common choice for this approximation is normal distribution with mu and with mean mu and variance sigma. So I say, okay, epsilon is a white noise, and then z equals just a linear combination of mu and sigma, and this mu is the mu and sigma are the outputs of the encoder. And I still have this. So I still have this stochasticity.
So how does this example make it simple? How we can get rid of that expectation?
Sorry, can you repeat the question?
That's actually the next slide.
Yeah, okay. So you'll see here. Okay, so this is, so now I can use Monte Carlo estimates of this expectation. And remember, these are those equations that I showed you. So these are my lower bounds that need to be optimized. For example, I have to maximize. Actually, I have to minimize. What was it? Okay.
So it's the difference.
To be maximized, yeah. To be maximized, yeah.
You want the difference to be maximized?
The lower bound should be maximized.
You maximize the lower bound, and you minimize the
KL divergence, yeah.
Yeah, it's a
The KL divergence should be minimized, so the lower bound should be maximized. Yeah, we want to maximize the lower bound because, again, P of x equals lower bound plus some kind of the KL divergence. And so this is the lower bound. If you maximize this, means you are maximizing the marginal likelihood. So this is what I'm going to maximize. And but again, I want to find a representation to simplify this. And back to the sampling process, if I have expectation of this, I can, using Monte Carlo estimates of expectation, it can be rewritten or represented with this. So it's just, for example, I take samples from this. I take samples for this deterministic variable with respect to this, and I can add them. So if the KL divergence is intractable, the entire thing in this bracket should be kind of so f is the entire thing in this bracket, or if the KL divergence is tractable, has a closed first solution, and if we use Q as Gaussian distribution, so it results in tractable KL divergence. So I will get this. So this is tractable. It has a closed form solution, so I'll put it here. And then this is my f of z, which needs to be estimated using MC. So this is actually the loss function for variational autoencoders.
So the idea that we put the function, deterministic function, is that it helps us to know what the sampling outcome
Yes,
will
actually
be.
I'll show you. There's a very nice picture that I took it from from the Kingsmont talk for NIPS 2015. So it explains why, you know, again, look at this. So this is the original form, and this is the reparameterized one. So you see that Z here is no longer random, it's deterministic. And the input is random. So because I'm taking derivative for the nodes. So this is how you can solve the problem and do backprop. And again, back to this one. So just one thing that, the reason I put all this stuff, because the VA is explained, you know, in blogs, but none of them really kind of explain that what will happen that you, from here, from this loss function, you get to the one that I will be showing in the next 2 slides. So this is the loss function for one point. But we're talking about big data, so we want to find the loss function for entire data set, let's say that based on mini batches. And it says that if M is large enough, you can put L1. So you don't need to take, you know, 100 samples, because the data is big enough, so you can learn about its complexity.
What was L again? Sorry.
So L is the, you know, L is the number of sampling that you do for Monte Carlo. Monte Carlo is, you know, when you want to find this expectation, there's an integration, and the integration is not tractable, they usually use Monte Carlo to take samples. For example, for this one, let's say, actually, instead of the Q thing, it's just a simple P of X. And then what you do is that for your input of the function, you take samples from, let's say that you know about this distribution, you take samples for the Z, and then you just add them all together. So that's why L is 1, and okay, so
is there an advantage of taking larger L's, or like is there a
because if you have, let's say L is 100, it means that you should do this 100 times.
My question is like is there a performance difference between taking one or the other? Like, for example, do you gain speed if you take larger L, or do you lose speed?
For a variational autoencoder, you mean, or in general?
No,
in general for MCMC, the larger the L, the better result you will get.
No, I mean
for this one, I haven't tried. So all of the loss functions that they're available, the L is 1. The thing is that the Z, the latent variable is just the summation of mu and sigma, and you don't take different samples. You just do it once, right? You can try. Let's see.
The way you can think of L is you do the reparameterization trick, right? Mm-hmm. So you do your encoding, and then you do the reparameterization trick, and then you do your backpropagation. And if you say I do L 100 times, you do the encoding 1, and then from the drawing, you just do it 100 times. So you do 100 times to the end, and then you take the average of all those 100 runs for your one cost function, then backpropagate it 1. So if you select the larger L, the slower it gets. The argument they make is, 1 or 10 doesn't make a difference.
Like the question is sure that step will be longer, but is the convergence faster?
I don't think so, because you can always run multiple epochs, right? So you can just run through the same data over and over and over again. It's more or less the same.
And in case of, I think, neural nets, because there are 100 epochs or whatever, you are basically doing this L. You're doing sampling. Mm-hmm. It's somehow, you do the same thing.
Sure, but I don't see, that doesn't say that one is better than the other.
Kind of like from the randomness portion of it, like if you do for each epoch, the randomness will be different. So the kind of the idea is saying is like, would you train it using, like when you have a set of examples you're using, are you going to train all those with one specific set of random parameters? Or it's like, are you just going to use the one example with lots of different random parameters? Is kind of just as a...
I have one question though. What's the big N? You say n divided by m.
Oh, this actually, this is the number of, actually, I think this is, I should put m in the denominator. This is, one of them is the number of the batch size and the entire number of data points.
Oh, okay.
The total number of data points, yeah. So it somehow shows that we can use mini batches, you know. This is, so the paper wants to kind of make the stuff ready for using deep neural net for this. So we can use mini batches, and if it's large enough, as far as I remember, it's the large means 100 or something, you can put L equal 1.
So, sorry, it's not the case that because we imposed already a structure to this z variable, by, for example, putting a Gaussian, so we already know how it would behave by sampling. So if we sample once, that would be okay. Is that somehow, rather than doing it multiple times to understand, okay, this is distribution is Gaussian.
But again, if let's say that you're not using deep neural net, if you want to just, you're not using variational method, if you want to use a stochastic method and Monte Carlo, you still have to do sampling, even if it's Gaussian.
Although your Gaussian maybe in Gaussian shape, but the parameter will be varied. If you have a sample and use that sample to estimate your parameters and use that parameters to compute the several losses and then back propagate for your parameters into the Gaussian distribution and then update the parameters, and the new Gaussian will be changed.
But paper says that since the size of mini batch is big enough, we can put L equal 1. So yeah, so then we have the loss function, again back to, okay, so again here, if we can say L equals 1, so it's just this scale divergence plus this reconstruction error cross entropy, the output of the decoder. So you take the mini batch, you sample from, for epsilon, you sample from a noise, and then you do forward path and compute the L, and then take the derivatives to find for back propagation, and you update the parameters. So the example is for the distribution of the latent variables, we assume that they have the zero mean unit variance Gaussian distribution. And for the likelihood, again, Gaussian distribution, same for the posterior, and for the Q, that oh, 5, yeah, sorry, thank you. Yeah, it should be Q5. And then, yeah, here, this one. This is Q5. And then the loss is just kind of this likelihood plus scale divergence for the latent variables that we want the, actually I made a mistake here too. It should go this, the Q should be here, for sure, yeah. And then, so the posterior, we want it to be as close as possible to our prior assumption. And if you use this, you just Gaussian distribution, this is your loss function. It's very tractable. There's a closed form solution, and you can use pixel differences in the case of image. Or you can use just the cross entropy as you use for autoencoders. And yeah, so the X will be fed into the encoder, and then you take the mu and sigma. These are the latent variable, deterministic latent variables. And somehow they're sampled, and then actually this is our latent variable that is just the deterministic function of mu and sigma. It will be fed into the decoder, and then you reconstruct your input. So, okay. So this is the latent variable space, and so this is, I just trained this model last night. It's only for 50 epochs, and I used those. It's on MNIST data, and this is the distribution of the latent variables. And so all these clusters, each cluster represent one digit, and you can see that the latent representation is very smooth. It's quite smooth, and you can see the smooth transition. And this smooth transition will result in having gradual morphing digits. So I'll show in the next slide. And for example, from here you can say that, for example, this represent, I can't see the colors very well, but this should be 0. And we can see that even, for example, in the latent space, 0 and 6 are very close. And then this is, I think it should be 1. But so this is one of the contribution of this paper. And as
What is the dimension of the Z?
so it's 2. It's 2 now. It's just 2. Z1, Z2. Yeah. And okay, so again, so I just trained this on Kara, so it wasn't a hard thing to do. So again, okay, now let's look at VAE as a generative model. So let's remove the encoder part and just having a decoder. And for the, so this grid is the input to the model, and the kind of the input data are the Z. Actually, the sample data are from -4 to 4. They were sampled at equal interval. They were fed into the model, and this is what was generated by the model. And you can see the gradual morphing, you know, of the digits. You know, these are they might not be even. They're not written by humans. They're generated by the model. So you can capture all these variations and the smooth transitions between the digits. Miss anything? And actually, there is a demo. I'm not sure. You can't see it, right?
Oh, you got to move that window to
Yeah.
slide it to.
There you go.
Right, there we go.
Oh.
Oh, that almost made it.
Okay.
Just change the parameters.
Yeah. So so these are the kind of okay. So what it does is these are the for example, for all these digits. So for the latent the dimension of the latent variable here is about 1, 2, 3, 4, 10. It's 10. And so for example, if I So by as far as I remember for this demo, let me remember what it's doing. Okay, so it reconstructs the. So okay, so actually it shows for example it samples. For example, if I click on 0, it takes a sample from a latent representation for 0 and generates kind of a sample for me. This is what it does. And then I can also play with the slides, and by playing with the slides, so I'm sampling a different value. And it doesn't necessarily mean that it has to be 0. But so the difference is that when you click on digits, so it takes a sample from the already trained, already learned representation. But when I play with the slides, so I move around, I hover around, I might go to the representation of the 9 or 8 or 5. So these are the latent variables. It's 10D.
Theta, fly.
No, these are Z. Yeah. Okay.
So the way I understood it for these kind of pre-trained classes, we have 0, 1, and 2. What they take is they take all the 0 classes which are labeled and then take an average of all the latent spaces. So you run your encoder part for all the 0 labeled ones, and then you get like a list of mu's and sigmas, and you just take the average of it.
Yes, exactly.
And
Yeah.
then you get the average vector or the average
Yeah.
representation.
Actually, yeah.
0 and 1 to show us how the slides change, for example.
Yeah, yeah.
And
Oh,
then-
here or actually, what I can show you is that. So yeah, you train and you take the average on this,
So
and this
these
is
does correspond to, for example, different types of zeros written by different people.
exactly the variation. It captures, let's say that this is for 0. It captures all the variations for the 0 that where the model has been trained on. Okay, so this is for test set, and it's for 1,000 samples. But if I want to use a VAE as a generative model, if I use one of these, so I'll get exactly what the model has been trained on. But I might say I want to take something like this, and you remember the grid that I used was in the same dimension. So if I use something here, the model hasn't been trained on that one. But, or might be, because I'm not, actually if I show the training set, I can say for sure that if the model has been trained on. But it will generate a sample for me that might have, that nobody has ever kind of has done it before.
0 or nothing like that. No one can recognize what it is, right?
Yeah, it could be a very different number. As you see that here. So, some of them are not.
Just symbols, but doesn't
So
mean-
here, this one, this is nothing. It's a transition from 0 to 4, but this is kind of.
So if you go to the previous slide, sorry. So what it essentially tells us that the right amount of domain that we can sample to get it.
Yeah,
that we
and
want.
yes. And basically, this is my prior, all these latent variable. If you draw the contours, you'll see that they all have, actually it's clear here, the contours, they are having 0 mean unit variance.
So the people in between, for example, so there are people who have bad handwritings, right? Hard to recognize.
We try not to judge.
Here the color indicates different clusters, right?
Yes, each digit has its own cluster. And again, because this is, actually I can't talk for autoencoder because it's not here to compare the results, but this is another thing that you can see, they're not isolated. The clusters are all kind of together, and that's why we put a regularizer. We want them to be close, and we want them to be within these bounds. We are somehow restricting them to have 0 mean.
Can you explain the creation of the regularizer in
The KL divergence one.
I get the reconstruction also over there. I did not get the regulation in the intuition, something like that.
So about logistic regression. So when you want to optimize or maximize the likelihood, so you can use gradient descent, whatever. You remember you add a regularizer term. What does that mean? You restrict your weights not to explode, or you somehow.
Yeah, but here this is.
Yeah, you're actually here. The reason I'm going to this slide is that one there was a mistake with. Okay, here. So your bottleneck here, the latent variables, you are making some prior assumption. And when you want to approximate the posterior, you somehow force the posterior to be close to your prior assumption. So this way you restrict them. Okay, I think we're good for the, so summary. So The idea behind the variational autoencoder is rooted in Bayesian inference and estimate. So the idea is that we want to find the truth distribution for our observations, and is a generative model with continuous latent variables. It's simple, it's fast comparing with Monte Carlo, Markov chain Monte Carlos. And the application is that they can be used for deep generative models, for example, for generating images, missingness, or adding noise, reducing noise. And then it could be also used for variational Bayes inference. Okay, again, I want to leave it to the discussion. Yeah.
Let's maybe take a 5-minute break.
Yeah.
And then let's come back.
Okay.
Sure.
So, okay, I don't have many slides for the discussion because I thought that it's something that we all gonna take part. So feel free to jump in and kind of raise stuff. Yeah. So now I'm forcing you guys. Okay, so so this is one of the hot topics these days, deep generative models, and there are. So the idea is okay. So the idea is, again, so let's revisit what we covered in the first few slides, is that we have some observations, and these observations are samples from a true distribution that I have no idea what it is, but I want to find it. So I'm trying to kind of find, kind of model this true distribution to generate some distribution that is closer to the true distribution. And so with these deep generative models, not degenerative, deep generative model is that if I can design a model that can take a unit Gaussian noise, pretty much a noise, and can kind of generate this green distribution, which is close to the right distribution, so I'm good. I'm done. So, and then at the beginning, the way model works is that at the beginning, you will see that this generated distribution is very far from the true distribution, and then at the training is done, it gets closer and closer to the true distribution. Again, for example, these are the regions that we believe that kind of our data points are belonging to. And I got this from the OpenAI blog on generative models, and it has a very good review of the three main approaches that are out. And yeah, so just to find these theta parameters, that gives me the true distribution. So there are, okay, just before I go to the next slide, so what are the three main deep generative models that are out and people are using by the Google, OpenAI?
Like generative?
Yeah, generative.
Yeah, GANs.
GAN, there are three. It's a hint. Yes. So VAE, GANs, and pixel RNN. So hopefully we know what the VAE is. So what about the GAN? Does anyone want to explain GANs?
This is my favorite.
Yeah, maybe, yeah. Actually, when I saw you today, I said, okay, he should lead that part. Yeah, so actually I can, so yeah, I have a slide that compares GAN and VAE. Maybe you can you please explain GAN to people? It's your favorite, yeah.
Should you prepare for your talk?
So just one can start and the other can jump in. And
So why are GANs better or worse than the?
yeah, actually I should have removed those. I should have showed those later. Yeah, I have. Okay, covered.
Chris.
Yes, as an initial example, for GANs, you don't have an explicit PFX.
Yeah. So maybe you can walk them through what the GAN is, and then.
So you have a distribution Z that you like random created set of variables that you feed into a generator that creates an image that you have one network that is a generator to create these images and one network that is a discriminator that tries to determine the difference between the real images that were created and the fake images that are created. And throughout this process, you end up creating a training set for a generator that creates images that are very similar to the image data set that you're given. But I guess you have to train, well, I guess in both cases you have to train two models. Apart from that, I guess there's some really good explanations as to why one's better than the other.
Yeah, so GAN is pretty much a game between two networks, between a generator and discriminator, and at the end, hopefully the generator wins. And if the generator wins, then it's good. It's an equilibrium point. And so one of the problems with the VAE is that the reconstructed inputs, so let's talk about images. They're very noisy and blurred, but with the GANs, the images are very sharp. But touching on what Chris mentioned, that the training is very unstable, so there is some difficulties with the optimization. And with the VAE, we can infer the latent variables. We can approximate the posterior, and we can find the distribution of the posterior. But in GANs, if we're going to do that, we have to backpropagate to find the posterior. So basically, there is a Bayesian involved here. So if you're interested in probabilistic models, so VAE is your model. Otherwise, GAN.
I think one of the concerns with GANs were that kind of the posterior overfits. So you saw before with the smooth images where you draw from the hidden state. For Variational Autoencoder, you see these smooth consistent with the numbers, whereas for GANs, they're like more abrupt changes and more like overfits, like a lot of like local areas where it tries to stay. And I think last year, Goodfellow published a paper on a trick how to improve that by just changing how you draw from it.
The CGAN or the CGAN?
I had to look it up. I don't know the title out of my head. I just
I think they just changed the laws. They did not use the Hill divergence. I think they are using the Earth's moving distance and trying to minimize the search area of the model in the GAN. So
yeah, let's.
But Florian, sorry, how we are going to be sure that if we apply this prior distribution, then we are underfitting the problem? How are we not sure? Do we have any idea whether it's underfitting or not? Because we're already imposing this structure, for example, it's a Gaussian structure, and maybe it's reality is not. So.
Oh, I see.
I mean,
well,
you can have it, for example, a GAN structure which is, although it's not stable and it can be overfitting, but it may better capture. How do you say, okay, this one is overfitting, this one is not in that space?
So
one of the problems that shows that it's not underfitted, but it's not like perfectly matching the posterior, is that blurriness. So when it's blurry, it for sure tells you that it's not perfectly finding the posterior.
Oh, for the VAE you mean, or the?
The difference between VAE and GANs, in the VAEs you have this prior distribution and you try to estimate the parameters of this prior distribution, right? But in GANs you don't have that, but you try to capture structure of the data by applying through the weights in deep learning sort of framework or something like that. You have this architecture.
But the prior also is the prior distribution. That kind of prior distribution also can be the neural network.
But in there we have this Gaussian type of.
Yeah, they are using Gaussian, but if you want to use it,
exactly. The question is like. With GANs, we are also trying to have a prior, but this prior is more flexible. We better capture the data. What we mean by prior is that you're applying a neural network over there, rather than just putting a Gaussian over there to try to put it, compress the data.
I've just seen in some examples to show why, I think that the term mode collapse is kind of like one of the examples. I might be using the term incorrectly. Is that?
Yeah.
Mode collapse is like if you were to visualize what you're putting into the generator as two axes, let's say two different variables. If you were to change one of the inputs that you're putting into the generator and kind of like just look to see how the image changes over time, you won't have this in a VAE where there won't be a change between one image to the other. Whereas like in a GAN, you could have an entire like range of inputs, like all collapse to the same image, I think.
Can we iterate that? Sorry, can we iterate it against it?
Oh yeah. So when you're looking at a change in an input parameter over the change in the output image, for GANs you could have something called mode collapse, where essentially the entire distribution of all those inputs will create the same image. Whereas with VAEs, that it tends not to happen in the way that the distributions are created.
Actually, I can show it.
This is exactly what I wanted to say before. What is mode collapse? So So you put different input, like this random noise at the beginning, it's a different one, but it will generate the exact same output.
Where's my mouse? Do you see it?
That's up there.
All the way in the top.
History? Like in
Oh,
there.
okay. So this open you guys continue.
Does someone explain does anyone have some intuition behind the blurriness, the reason for the blurriness? Like, is there a deeper explanation for this?
I think you approximate the posterior, right? So the posterior is actually how the data was generated from the statistical process behind it. And you just approximate it. So if you approximated it perfectly, you would generate unblurred images. But because you have some loss, or you're just approximating, depending on what you are, you have more or less blur. And VAEs are not as good. Or let me say this, they're not punished severely when they just do a good approximation. As with the GAN, the discriminator can very easily discriminate working and non-working.
Okay.
So given this blurred image, how is preferred compared to GAN?
Excuse me?
Given this blurred image,
Yeah.
it seems that there is an approximation in the distribution. How is preferred sometimes compared to GANs? What's the rationale behind it?
What is your goal?
I think the most important thing is that the interpretable, like latent space, because sometimes you wanna know if I changed like this Z1, this is what is changed at the output. Like.
And for compressing, I'm not sure if they use GAN for compressing, but you can use VAE for image compression. I know about in medical fields that when they work, sometimes they work with high-res images, kind of not comparable 20,000 pixels by 20,000 pixels. They have to compress images. So it has a good application for those because you need to reconstruct the images, do some stuff and reconstruct it back. Other than that, for noise, they still use GAN. For missingness, I think if you mask some part of the image, they still use GAN to generate because it gives you better quality.
Sorry, I'm just asking out of curiosity. I'm not sure whether the question is correct or not. But the thing is that your background is electronics, right?
Yeah.
So I know something about this Fourier transforms, that what it does is essentially getting this, like this, for example, frequency as a way to represent the whole
Exactly.
distribution.
Yeah.
This is the same idea behind it, that we want to somehow approximate it, for example.
So not this one, but you can see deep learning as something similar to Fourier transform, because in Fourier transform, you transform signal from time domain into frequency domain, and those different frequencies are your latent variables. But it's just one single transformation, but we are talking about different layers in a deep. The depth is kind of more. It's
approximate this frequency, you need to.
Yes, actually we do this in communication to, what did we call it? For other than compressing, we had a carrier, an envelope, and
OFDM? OFDM?
yeah, but the modulation.
Modulation.
Yeah, modulation. So.
My background is not electronics.
So, do you wanna I can explain, but maybe you can give me a better.
So the idea is the whole information that you have in time domain, you can transfer it in frequency domain because you have better representation of your time domain signal and frequency. Then you can apply any techniques like you can add filters and everything. Design-wise is much simpler than treating the system in the time domain.
For example, in terms of convolution, you can do multiplication if it's in a different domain.
So there is this area of dictionary learning. So what it does is that it says, okay, there are some spaces that you can define your signal in a sparse way. So you can compress the information, so you don't need to know that much about your signal. You know general information about the dictionary which is representing your signal. For example, Fourier domain is a general kind of dictionary because it's applicable to almost all kind of signals. Or you can learn dictionaries from the signal.
And I'll give you an example from brain signals. Say like if you don't, it's really noisy, right? So we only want certain parts of it and take out the noise, so we can denoise it much easier in the Fourier transform.
And I think so you were saying like when you're applying it to this, like a really good way to think of it is if have you ever seen how JPEG compression works and how when you look at an image, like really sharp distances between color contrasts or like would represent like higher frequency like information, and you can represent an image to a really high like degree of like validity, like to its original representation, using only like a smaller set of those lower frequency representations that might not have the really sharp edges. And so when you see the blurriness, it's probably just like finding, in essence, like a lower, like
yeah, let's say that you have a filter and it's some of the frequencies are not captured by that filter. Let's see.
Blurriness, could it be also due to the loss function? So like because you're setting the loss function for the VAEs, and the GANs you're generating a loss function, hence it's able to produce the sharper image.
That's a good point. Yeah. Because of the loss function in the BAs, you mentioned that it's pixel-wise, right?
So exactly, and then yeah, you add them all together.
Yeah, so like pixels that are nearby will have a relatively close.
Yes, the corresponding pixel. Yes, yeah. So the loss in terms of regardless of the KL divergence, the cross entropy or the reconstruction error is pretty much like what you do for the simple AE. Pixel by pixel, yeah.
It's pretty cool.
For generating the distributions and training, is it a convention to use normal distribution?
No, you can. Actually, you can for that. So the paper recommends that because we are talking about two different distributions. For the posterior, QZ given X, and then PX given Z, the output of the encoder and decoder. So it says that for the output of the decoder, the actual output of the model, you can, if your input is binary, use Bernoulli. If it's more, you can use Gaussian. But again, because Gaussian is tractable, that's.
Another advantage is that for the Gaussian, you have mean and variance. That is very suitable for the reparameterization.
Yes, 2 parameters.
That is bad. That's very good for the back propagation in the neural network.
Yeah.
But this representation trick just works as well with like Bernoulli or Invariant or whatever. You mentioned in a paper how to do it for the other distributions.
It's impossible. Yeah. But the math you need to, because another point here is that when you're using sample to train this neural network, you can train, but the thing is you have different samples that the sample out the hash with there is great variance over there. That is the parameters change will be shifted a lot, like great variance. If you're using this kind of Gaussian, this is good for that one as well.
So even in Bayesian community, most of this stuff is in Bayes, like a Gaussian distribution.
Because the key of Bayesian is uncertainty over there.
Yeah, even in communication, I remember white Gaussian noise, everything.
This autoencoder essentially is like trying to transmit a signal, isn't it? That you're trying to pass it through this latent space and then try to understand whether it's correct or not. So that's what is this analogy.
Sorry, I missed your last point?
You know, the thing, I think what this autoencoder and decoder does essentially is that you're trying to send a signal through this latent space, and then you're trying to say, okay, how can I
reconstruct it back,
again?
yes.
Okay.
As you do with the PCA. And actually, no, PCA is mostly for dimensionality reduction, but the way that kind of you optimize it, even it has a closed form solution, but it's that you look at the reconstruction error and you take the derivatives of the reconstruction error. Yeah. And then there is a pixel RNN. Do you want to talk about pixel RNN? There's a...
I remember that I read that one in DFA's slides over there, 3 of them. It seems that is the assumption over there is that there is a tractable density of the distribution over there, and that is a tractable density distribution, and another one was variational estimation with the V, another one was adversary estimation with GAN. This is really important. This is the point I can remember from that slide.
Yeah, so for pixel RNN, let me find the image that explains.
I think it showed images for pixels instead of.
No, I'm looking for the...
No, but look,
Oh, so
there's a
just
typo. Yeah. There's a typo in the name.
So it's what it does is that so far for all these actually you touched on that point that, for example, we are talking about all these deep generative models for the application on images.
The second column is the force.
Maybe that's why it doesn't come.
I think you.
No, you're looking for CNN.
Oh.
You can
Can
search
see.
into a pixel if you correct the search term in there.
Yeah. Yeah, that happened again.
Mhm. Okay, yeah, I was looking for that. Actually, not that one. There's a, okay, so yeah. So what it does.
Can you zoom in a bit?
Just do command plus. Yes.
Okay, so back to VAE and GANs. We did pixel by pixel, but we didn't really kind of consider that all these pixels are dependent. So what pixel RNN does is using recurrent neural net. So actually the P of X is defined in a way that all these pixels are conditional dependent. So it uses LSTM or RNN, but both vertically and horizontally. But it's not very, because it's too slow, I think, using RNN. Maybe these days they can use transformers. So, yeah, they can like a language every 2 pixels, how they're connected. The relation between the pixels.
Pretty
Yeah.
sure the paper already exists. This is my attitude. If you think of
For
something,
sure it exists.
If you think of something, it already exists.
Yeah. Actually, no way that you can find a paper and have an idea that hasn't been taught before. Or
Just go to a really obscure subfield of something.
Any other discussion?
no, I'm good.
So
Yeah. Thank you.
Yeah.